over 370. And that will give me a lower frequency.
404.3 hertz.
So it goes from roughly 483 to 404. I really don't know what the frequency of a car horn is, but let's see if we, how well we can
Frequency
simulate
not
this.
found.
Pardon?
404, file not found, I was just making a joke.
Oh. Sorry, I missed that.
Yeah,
Hopefully I'll remember it and use the same numbers next time. Pass it off as my own.
and,
They say they typically pair over 420 to 440 or 340 to 370.
So 440 is not unreasonable.
Yeah.
All right. So as it comes towards, so here's 440, here's what you hear as the driver. So this will be 404, and this will be 480, was it?
482.6.
Comes towards you, and then away. Yeah, that's not as good as I was hoping, but
And the amplitude's gonna be way louder.
yeah, the amplitude end will be increasing as it comes towards you.
Yeah.
Now notice though, this is not the same thing as if the observer were moving. Any questions on this before we switch it around and have the observer move? So. So now the receiver will be hearing a higher frequency because he is hitting these wavelengths sooner. So if he runs towards and is still observer, the question is, what is the period between his receiving these? Because once I have the period, I can get the frequency. So if he hits the first pressure wave here at time is equal to 0, he's going to hit the second pressure wave at a time is equal to T sub R. Because this is what he is sensing here. If he's traveling at some speed V sub R, because I have the waves traveling to the right, so at time is equal to 0, I got the first wave front here, and he is here. And the second wave is here. And then he runs this way, and the wave is traveling in that direction. So this would be the speed of V sub R, T sub R. This right here would be the speed of sound times T sub R. But the distance between the wavelengths, remember the distance between the wave peaks is based upon what is produced. So this is the wavelength from the emitter's point of view. So CSTR plus VRTR equals lambda sub E. So CS plus VR times TR is equal to the speed of sound divided by the frequency from the emitter's point of view. The period is the reciprocal of the frequency, as just mentioned earlier, plus VR, divided by the frequency from the receiver's point of view is equal to CS. And now again, we solve for FR. It's gonna be FE times CS plus VR over speed of sound. And again, we've defined VR so that they are getting, the source is running at the car. So, let's go to that example again. The car is blowing a horn at 440 hertz. This is the frequency from the emission. And this time, you're on the side of the road running at the car at over 60 miles an hour because you are that good. So the frequency that you will hear if you run at the car at that 30 meters per second is going to be 440 times 340 plus 30 divided by 340. And then as you run away from the car, it'll be 440 times 340 minus 30. 340.
That one will be 478.8 hertz. And the second one will be 401.2 hertz.
We got the same numbers?
I got the same thing.
All right. So compare that to the other one, which was 480.6 hertz with a car coming towards them, and then 404.3 hertz when the car is going away. There's,
I'm sorry, almost the same but slightly different.
yeah. The key thing is the fact that they are different between how it's produced or how it's received. Now, obviously, we have a scenario here where car is moving, receiver, person is still, and then person where the person is moving and the car is still, but obviously, the other option is they're both moving. I'm not going to go through the derivation, I'm going to sort of hand wave it, but we'll combine the two formulas. So the frequency that will be received is equal to the frequency that's emitted, and then you'll have the speed of sound plus minus the speed of the receiver over the speed of sound minus plus the speed of the emitter.
And which one is, this is for the receiver?
This is, if this is the frequency that the receiver gets, is equal to the frequency the emitter gets, and then speed of sound, and then if the receiver and or the emitter are moving.
Yeah. Whichever one's moving, you just take away which one's not moving.
Right, or if they're both moving, you keep them both. But the trick is, and I've seen this formula a lot of times, and then there's a chart about when to use plus, when to use minus. And to me, those charts I find very frustrating. One, for some reason my brain just doesn't work that way of trying to memorize a chart. I hate memorizing. Just remember, if the car is coming towards the person, the frequency should be higher. Well, this is the one dealing with the car or the emitter. If the emitter is coming towards me, that should be a higher frequency. Well, I get a higher frequency by having a smaller denominator. I'm going to subtract. If the emitter is going away from me, I should get a lower frequency, and so I'm going to add the denominator. Up top, if the receiver is coming towards the emitter, then I should get a higher frequency, so I'm gonna do a plus up here. And then if it's going away, I should get a lower frequency, so my numerator should become smaller. If you think through it, at least for me, thinking through it is much better than any table or chart I've ever seen.
Yep.
Or you can create your own chart to memorize that, but the less memorization for me, the better. And on that note, so on Wednesday, we're gonna do the lab, but the first thing we're gonna do on Wednesday is discuss sort of the first test and when that's gonna be. And I think on that note, be safe. And yeah, don't go into quarantine. Well, go into quarantine if you have to. I want you to come to class if you need to stay home. But don't put yourself in a situation where you need to be quarantined. Please.
I have a question about, this, which one of these would I use as the x-axis, which is the y, for graphing?
All right, so what plot are you trying to make?
You said to use a scatter
What
plot.
do I say? What versus what?
First point.
That's procedure A, right?
Yeah, it is procedure A.
Plot, average position of last loose coil versus hanging mass.
Oh, okay.
So this will be the average position. And this will be the mass.
Okay, so this will be y, and then this will be x.
Yeah,
Now,
vertical and horizontal.
Okay,
It's not the y-axis, it's the average position axis.
okay,
It's not the x-axis, it's the hanging mass axis.
okay.
and would you like separate graphs or put them together? Like the other procedure, that's procedure B, I think procedure E is the same, just repeat it, do you want to put that on the same?
All right, so it's 5 graphs. The graphs need to be large enough for me to be able to see the detail.
Okay,
But don't, because the person that I basically took all this from, at least my starting point, was Nick Vonnebeck at CPCC, and he wanted 1 graph per piece of paper. It doesn't have to be that extreme, but just, they need to be big enough for me to see.
okay.
And labeled so I'm not going, wait, which graph is this?
Yeah. I use the printer at work, so it's no cost to me, I'll print out.
Oh, okay.